Black holes have always fascinated scientists and the general public alike due to their immense gravitational pull and mysterious nature. In the 1970s, physicist Stephen Hawking made a groundbreaking discovery about black holes, suggesting that they aren't entirely black and that they can emit particles. This phenomenon is known as Hawking radiation. Hawking radiation arises from the principles of quantum physics, which govern the behavior of particles on a microscopic scale. According to quantum physics, particles and antiparticles can spontaneously appear and annihilate each other, forming what are known as virtual particle-antiparticle pairs. Normally, these virtual particles quickly vanish, leaving no observable trace. However, near the event horizon of a black hole, things get intriguing. The event horizon is the boundary beyond which nothing can escape the gravitational pull of a black hole, not even light. Hawking proposed that at the event horizon, one particle from a virtual particle-antiparticle pair can fall into the black hole, while the other particle escapes into space. This escape of a particle is significant because it carries away energy from the black hole. Since energy and mass are interconnected, as described by Einstein's famous equation, E equals mc squared, the loss of energy results in the gradual decrease in the black hole's mass. In other words, black holes can evaporate over time through the process of Hawking radiation. This concept challenged the prevailing notion that black holes are eternal and can only grow in size by consuming matter and energy. Instead, Hawking radiation suggests that black holes can slowly release their mass back into the universe. It was a remarkable breakthrough that opened up new avenues of research and sparked further inquiries into the nature of the universe and its ultimate fate. Hawking radiation, while intriguing, poses a significant challenge for observation and measurement. The emitted radiation from a black hole is incredibly faint, making it extremely difficult to detect directly. However, scientists have simulated the effects of Hawking radiation in laboratory analogs using various experimental setups, such as water waves and sound waves. These analogs help validate the theoretical predictions and provide insights into the evaporation process. Quantum physics takes us into the realm of the incredibly small, where particles and energy behave in strange and unpredictable ways. One of the fundamental principles of quantum physics is the existence of quantum fluctuations, even in seemingly empty space. Quantum fluctuations refer to the spontaneous and temporary fluctuations in energy that occur at the microscopic level. These fluctuations give rise to the creation and annihilation of virtual particles. Now, virtual particles may sound perplexing, but they are an essential concept in understanding the evaporation process we are discussing. Virtual particles are particle-antiparticle pairs that spontaneously come into existence due to quantum fluctuations. They are not directly observable because their lifetimes are incredibly short, but their effects can be detected and measured through various experiments. Imagine a vacuum, which we often think of as empty space. According to quantum physics, even in this vacuum, these fluctuations occur. Energy can momentarily borrow from the vacuum, resulting in the creation of virtual particle-antiparticle pairs. These pairs exist for an extremely brief period before annihilating each other, returning the borrowed energy back to the vacuum. However, near the event horizon of a black hole or in the presence of strong gravitational fields, the fate of these virtual particles can take a different course. Instead of both particles annihilating, one of them may fall into the black hole while the other escapes into space. This occurs because the intense gravitational pull of the black hole alters the dynamics of the virtual particles. The particle that escapes carries away energy from the black hole, leading to the gradual loss of its mass. This process is the essence of Hawking radiation and the evaporation of black holes. It is important to note that the energy for the escaping particle comes from the black hole itself, reflecting the interconnected nature of mass and energy described by Einstein's theory of relativity. While the existence of virtual particles and quantum fluctuations may seem abstract, they have been experimentally verified. The Lamb shift, which earned Willis Lamb the Nobel Prize in Physics in 1955, demonstrated the impact of these virtual particles on the energy levels of hydrogen atoms. This experimental evidence solidified the reality of quantum fluctuations and provided a foundation for further exploration of their implications. In a recent study, scientists have presented a groundbreaking idea that expands the concept of evaporation beyond black holes. While evaporation was originally associated with black holes and their event horizons, these researchers proposed that similar effects can occur in other astrophysical objects under specific conditions. The key concept introduced in this study is the notion of the escape cone. This term refers to the steep curvature of spacetime that can generate effects resembling evaporation, even without the presence of an event horizon. While the event horizon still holds the highest likelihood of these effects, the scientists argued that it is not the sole requirement for evaporation to take place. The researchers suggest that certain conditions can cause an imbalance in the quantum waves associated with virtual particles, resulting in a higher probability of particle escape. This escape then leads to a transfer of mass or energy from the object itself, contributing to its gradual loss over time. Interestingly, the study doesn't focus solely on gravity as a factor for evaporation. While the idea of evaporation traditionally stems from gravitational effects near black holes, these scientists draw inspiration from observations involving electromagnetic fields. They highlight a phenomenon known as the Schwinger effect, which occurs in strong electric fields and leads to the creation of electron-positron pairs. Drawing parallels between gravity and electromagnetism, the researchers argued that if electric fields can produce virtual particles, then gravity should exhibit similar behavior. They suggest that objects with significant mass and the associated spacetime curvature, such as neutron stars, white dwarfs, and even massive galactic clusters, could potentially undergo a form of evaporation. While the study presents these ideas based on mathematical models and simulations, further investigations and future observations are necessary to validate these hypotheses. If confirmed, it could open up a new understanding of evaporation processes across various cosmic objects and reshape our perception of the universe's fate. If everything possessing mass, from black holes to galactic clusters, is subject to evaporation, it means that the universe itself may slowly lose mass over time. This potential evaporation of the entire universe would occur over an unimaginably long timescale, perhaps trillions upon trillions of years or more. This study paves the way for further research and exploration into the evaporation process in the universe. If physical observations align with the predictions made in this study, it would provide compelling evidence for the widespread occurrence of evaporation-like effects and prompt new avenues of scientific inquiry. The recent study takes inspiration from observations involving electromagnetic fields and the Schwinger effect. The Schwinger effect refers to the creation of electron-positron pairs in the presence of strong electric fields. This phenomenon demonstrates that virtual particles can manifest as real particles in specific conditions. Drawing parallels between electromagnetism and gravity, the scientists proposed that if electromagnetic fields can generate virtual particles, then gravity should also be capable of producing similar effects under certain circumstances. While the focus of the study is on gravity and its relationship to evaporation, the researchers utilized the Schwinger effect as a guiding principle. By applying the concept of virtual particles and their manifestation in electromagnetic fields, the scientists suggest that gravity can generate these particles in regions of significant spacetime curvature. This means that objects such as neutron stars, white dwarfs, and massive galactic clusters, which possess mass and create a curvature in spacetime, could potentially exhibit evaporation-like effects. While the study primarily focuses on the theoretical implications of this proposal, it opens up exciting possibilities for future observations. By investigating these effects in gravitational environments beyond black holes, scientists may be able to detect and measure the presence of evaporation-like phenomena. However, it is important to note that further research and experimental validation are necessary to confirm these hypotheses. Scientists will need to explore the mathematical models and conduct observations that can align with the predictions put forth in this study. Only through continued exploration and data collection will we be able to determine the true extent and implications of evaporation-like effects in various gravitational environments. The application of the Schwinger effect and the consideration of electromagnetic fields in relation to gravity highlight the interdisciplinary nature of scientific inquiry. By drawing connections between different branches of physics, researchers can expand our understanding of fundamental phenomena and potentially uncover new insights into the workings of the universe. The implications of the recent study extend beyond the realm of individual objects and into the grand scheme of the universe itself. If evaporation-like processes occur beyond black holes and are prevalent in various gravitational environments, it implies that the universe's mass can gradually diminish over time. This phenomenon would have profound consequences for the universe's long-term fate. As objects with mass undergo evaporation, they lose energy and contribute to the gradual dissipation of the universe. The steady depletion of mass implies a continuous transformation of matter into energy, eventually resulting in the complete evaporation of all massive objects. This breathtaking notion suggests that everything we know, from stars to galaxies, would eventually cease to exist as tangible entities and be reduced to minuscule particles and pure energy. However, it is crucial to emphasize that this process would unfold over an inconceivably vast timescale. Trillions upon trillions of years, or perhaps even longer, would be required for the universe to undergo such a transformative journey. It is a testament to the immense scales of time and space that the universe encompasses. At present, no direct physical observations have confirmed this evaporation-like process in objects beyond black holes. The study's predictions and proposals are primarily based on mathematical models and theoretical frameworks. Nonetheless, this opens the door for future investigations and potential observations that could validate or challenge these hypotheses. Scientists may explore methods to observe and measure the effects of evaporation-like phenomena in gravitational environments, such as neutron stars, white dwarfs, and massive galactic clusters. By studying the behaviors and characteristics of these objects, researchers may gather evidence that aligns with the predictions outlined in the recent study. Such observations could involve detecting subtle changes in radiation emissions or analyzing the properties of particles in the vicinity of these massive objects. Advanced telescopes and instruments may play a crucial role in unveiling the elusive traces of evaporation-like processes and shedding light on the intricate workings of the universe. While the future remains uncertain, the study's implications invite us to contemplate the vastness of cosmic evolution and the potential destiny of our universe. Understanding the mechanisms behind evaporation-like phenomena expands our knowledge of the fundamental forces that shape the cosmos. It serves as a reminder of the awe-inspiring complexity and mysteries that lie beyond our current understanding.